In this podcast, we're going to look at determining molecular polarity. So we're going to create a graphic organizer for you to follow to use when you are trying to determine if a molecule is polar or not. When you have a molecule and you're trying to decide whether or not it's polar, the first thing you need to do is draw your Lewis structure. After you draw your Lewis structure, you know which atoms are bonded together covalently. This is when you calculate your electronegativity difference as your second step. If you calculate that electronegativity to be less than or equal to 0.4, then you have a nonpolar molecule. And we know this because we've already learned that in order for a molecule to be polar, it has to have polar bonds. If the electronegativity difference is less than or equal to 0.4, then we know the bonds are nonpolar, and thus there's no possibility for a molecule to be polar. Before we move on, make sure you have this half of our flowchart copied, because now we're going to look at what happens when the electronegativity difference is greater than 0.4. If the electronegativity difference is greater than 0.4, we know a polar molecule is possible because we know the bonds are polar. Because we now meet one of those criteria, we have to look for overall direction or symmetry of our molecule. So our third step after calculating the electronegativity difference and we realizing it's greater than 0.4 is to check for symmetry and overall direction from charge. For symmetry by drawing an arrow from the slightly positive charges to all the slightly negative charges, and I'm going to demonstrate how to do this in a minute. If all the arrows go in the same direction, or there's only one arrow, it means we have a direction of charge or a magnet, and the molecule is polar. Now, if you draw those arrows and they happen to go in the opposite direction, then we end up with a non-polar molecule, or there's no magnet. There's no separation of charge. Okay, so make sure you have this copied down. We're going to move on and do a couple examples together in this video lesson, and then you will have some that you're going to need to work on your own. The first example we're going to look at is hydrochloric acid, and looking at our flow chart, the very first thing we need to do is draw our Lewis structure. So our Lewis structure, pretty easy for HCl, hydrogen bonded to chlorine. And we need those outer or non-bonding electron pairs on the chlorine. Our second step is to calculate the electronegativity difference. So our electronegativity value for hydrogen is 2.1 and for chlorine is 3.0. And we talked about how to get these values in our polar bonds lesson from our periodic table. So our difference is 3.0 subtract 2.1 equals 0.9. So because we have an electronegativity difference that is greater than 0.4, we end up with polar bonds. So our hydrogen gets a slightly positive charge and our chlorine gets a slightly negative charge. The next thing we need to do when determining molecular polarity is step number 3. We check for overall symmetry or overall direction of charge. So we draw an arrow from the positives to the negatives. So I usually like to make a plus and then carry it over towards the negative. In this case, we only have one arrow, and so because we have a direction of charge, we have a polar molecule. So HCl is polar because it has a direction of charge. Okay, and then just to tie this in, the geometry of HCl is linear. And if you're unsure how to determine molecular geometry, then you need to be visiting our module lesson on molecular geometry. Our next example is H2O, water. We already know how to draw our Lewis structure. We've done the math already in a previous lesson. So we know water looks like this. We know its molecular geometry is bent. And now we have to calculate our electronegativity difference. So hydrogen, once again, has electronegativity of 2.1, and oxygen has an electronegativity value of 3.5. So we calculate 3.5, subtract 2.1, and we get 1.4. So that means, yes, we have polar bonds. We've met one of the criteria for a polar molecule. Because we have polar bonds, we have to add our partial charges. Partial positives to hydrogen and a partial negative to oxygen. Now we have to look for symmetry, or overall direction of charge. Drawing our arrows from positive to negative, it looks like this. Our arrows are going in the opposite direction. It looks like they're going to the same place, but they're actually headed in the opposite direction. Another way to look at this is you can also kind of determine where the center of each charge is. So if we redraw our Lewis structure so it doesn't get messy, we have a partially positive hydrogens and our partially negative oxygen. The center of positive charge is in the middle of the two positive charges, so it'll be right down here. The center of negative charge is where the only negative charge is, right here. Those two are in a different place, and they look like a magnet. So because we have the arrows going in opposite charges up here, or you can do the magnet method down here, we know we have a polar molecule. Because it's asymmetrical. Or there's direction of charge or a magnet. The last example we'll look at is carbon tetrachloride. So we draw our Lewis structure. Carbon's our central atom because it's first in our formula up here, and because it has the highest bonding capacity. We've already done the math, so we know our structure looks like this. Now we calculate electronegativity difference. The electronegativity value for carbon from the periodic table is 2.5. And from chlorine, or for chlorine from the periodic table, is 3.0. So our electronegativity difference is 3.0 subtract 2.5 equals 0.5. So that's greater than 0.4. So we know we have a polar bond. So we've met one of the two criteria for a polar molecule. We add our partial charges. Chlorine has the higher electronegativity, so it becomes slightly negative. Carbon becomes slightly positive. Now we have to look at the overall geometry of our molecule and determine whether or not we have direction of charge. So if we draw our arrows from our positive to our negatives, They're all going in the opposite direction. So that means that we have no direction of charge. So we have a non-polar molecule. The other way to look at it, once again, is looking at where your center of positive charge and negative charge is. So those chlorines are still partially negative. The carbons are partially positive. Excuse me. So the center of positivity is where the only positive charge is, right here on that carbon. And the center of negative charge is in between all of the chlorine atoms. So that means the center between this chlorine and this chlorine is right here in the middle. And the center between this chlorine and this chlorine is also right here in the middle. So our center of negative charge is in exactly the same spot as our center of positive charge. So that means that there's no magnet here. So this molecule is non-polar. And just a recap, the shape here is a tetrahedral. And our tetrahedrals are usually nonpolar. Okay, so make sure you have this example copied down into your notes, and you're going to need to work through some practice at this so you can become proficient at determining molecular polarity.